be online already. Okay. First of all, the idea is, and one of the things that I'm trying to do with these notes is I want to put them up on like Jupyter Books, it's called. So then you create a book of your notebooks and put it onto some website somewhere so that it becomes like an open educational resource, which I think is like, it's not really specific enough knowledge. Like you could just Google around and basically find everything that I talk about, right? But it's all like kind of discombobulated. It's all different nomenclature and everything. So I do want to try and like put it together. And the library actually offers a grant program for us to do that and release it as like open education. So that's my goal. And then just like in future years, then I would just be able to do that. But I'm not so satisfied with the Jupyter book, the Jupyter Notepad format. I find it a bit ugly and kind of hard to navigate. So there are one of the other textbooks that I linked to. So I don't know if I have it on here. If not, I can open it up. I think it's this one. Yeah. This is also actually a Jupyter Notepad that's been kind of formatted through this tool called Jupyter Books. And I find this a lot nicer to look at. Like it has a search bar. It has everything is linked on the left-hand side. You can navigate easily. You can open up your files and stuff like that. So that's what my co-op was originally working on, but he's gonna jump into something else. But that's kind of the goal. And then like to actually have this stuff up, I'm trying to work out like how interactive I can make it while not being like having a Python engine running behind. Yeah, with the whole tenure thing, I mean, that's the whole point is you want your academics, like this kind of like goes back to the day of like the Greeks, basically, right? And like you want your academics to be free from like political minds and political influence, because that's the whole idea, like university area of thought. You don't want to have like, oh shit, I hope I don't, upset Trudeau. Like, okay, right? But like, so the whole idea with tenure is that once you get tenure, then effectively you are not able to be fired. That being said, I mean, you can always, you really screw up something, then you're going to be able to be fired or just killed in that case back in the ancient Greek. Fired out of a cannon. So I came in, so there are 3 levels to profs. If you come in as an assistant prof, then you have, I think it's 7 years to get tenure. The tenure process takes a year. So it means that you actually only have 6. I came in as associate, which is the middle one, untenured. So I only have 3 years to get tenure, which again means that I only have 2. So according to department chair Rafi Kleiman, he said I basically like I'm going to be evaluated on 3 things, right? I've got the teaching, supervision, and research. Because I've been working already, I've already got kind of my research chops. I need the teaching and the supervision. Student supervision. So JC is actually my PhD student. Yeah, he was under another prof before. That prof went back to Japan. So now JC is coming under me, which is super awesome because he's awesome. So yeah, so that's like normally new profs don't teach right away. They have like a year of teaching relief in order to develop their research program. But because I need to develop that, like I need the teaching part stat. That's why I have to like jump into teaching right away. But what he said was at least like he can promise me the same courses again next year, so I don't have to do all this prep work again while I'm doing everything like that. But yeah, teaching is interesting. It's good in some ways, but like it would be a lot better if I found a textbook that covers everything that I actually want to teach, instead of like rewriting every single lecture every single time.
So going to be like a 4 and 2 GM starting from now on, as long as you stay like
no idea how it works. At least for 2 years. I'm gonna push for longer because, to be honest, like having developed this stuff and prepped this stuff, I would rather not like jump over to another one, but I have no idea how it works. Absolutely not. So we'll find out. Ask me again in a couple years. Okay. Everybody online, you guys can hear me okay if I don't have my headset on, and maybe other people in the class?
Yeah, we can hear you.
Okay, it's good.
Yep. Perfect. Okay. So today we're going to start talking about differential equations. Differential equations are pervasive in like the natural sciences right across the board. There's a great quote from a mathematician down south. Since Newton, mankind has come to realize the laws of physics are always expressed in the language of differential equations. It's just all over the place. People use it for weather predictions. I think it was originally developed for like artillery. That was a big driver for like the early computers and calculations and stuff like that. But it's all over the place. The whole idea with differential equation, how much like you guys have all talked about differential equations? Would you know what I meant if I said like inhomogeneous differential equation, partial? Yeah, I'm going to go through. I just want to make sure. I just want to see where you guys are at. Yeah, so the whole point with it is that we're going to be relating a function and its derivatives in some way. Sometimes the function itself will appear. Sometimes only the derivatives will appear. It's a very general thing. It is a vast field. There are all kinds of tools that go into this thing and all different perspectives and techniques. There are new ones being developed every day. One that came out in the last few years is something called neural network PDEs. And the idea is that you have a different, the way of solving these. There are lots of new ways. So one of the newer ways is to do, is to fit or I don't know what you call it. You train a neural network for differential equation, and then you query the neural network for the answer. And the nice thing about that, well, first of all, everybody's all super excited about neural networks, but you also don't need to discretize. You can train a neural network on the form of the equation itself, which is kind of a neat idea.
What is in your
I'm not a good person to ask about this, but depending on what happens tomorrow, actually, with regards to the group project, I have an appointment with the McPherson Institute to talk about that. But I think it's possible. Just got to work out the logistics. So I'm hoping to let you guys know on Wednesday if like how that would work. The whole idea of a neural network, as I understand it, does anybody like specialize in neural networks or something? Wants to no? Okay. The whole idea of a neural network is actually mimicking our neural networks, right? And what is it? You have inputs into this box, which are your function arguments. And then you do stuff to it. And you can go through different layers. You combine the different inputs in different ways. I think this is a transfer function or something, right? You combine all these things into different ways. You get these intermediate values. All these guys are cross-linked. It's this big, weird way of looking at these things. And eventually you might have like several layers in between. All of this stuff is crossed in different fun and exotic ways. And eventually you get an output. Yep. Are you online, Stefan? Hello? I see you muted.
I think Stefan is trying to say something, but I can't hear him.
Stefan, we don't hear you. See if I can unmute you manually. Nope, I can disable your mic. Just one sec, troubleshooting. I can see your hand up. No. So in a nutshell, because we're already 20 minutes into it, the whole idea is every layer here is some combination of the layer above it. And that some combination is like a weighted sum or a weighted sum of some transfer function or something like that. And then you train it in order to determine your weights. And because these things can be big, 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 you know, that training takes a whole lot of time, which is apparently what Google Colab is actually designed to do, which is kind of neat. What it is in terms of how it's actually used, the best way I've heard it described is as a general function. So it is a correlation to the nth degree. Whatever you wanted to ask it, it could theoretically map out, which is neat because then you could do all these nonlinear relationships, right? And hence how our brains work, right? We take a bunch of signals and resolve it into a person, which is kind of neat. But then the value behind this with differential equations, haven't gotten much into that, but I would like to. At one point, if anybody's looking for like masters or something, that would be pretty cool. Or PhD. You don't need to discretize it, right? Finite difference, you have to have a regular grid. Finite element, you can at least get away from your regular grid, but you're still discretizing it. And the type of modeling that I do has a problem because you have big length scales and small length scales. And to resolve everything, you need to resolve only the small length scales, like the small length scales everywhere. And that gets super slow. But if you had a technique that didn't need that, that might be pretty cool. But again, hopefully as of tomorrow, we'll figure out a way to do that as a group project. And then if Stefan wants to describe it more formally for marks, even better. Excellent. Okay. So differential equations, incomplete list, starting at the top. First order versus second order. So all of these guys are not exclusive. They can all be doubled up and everything, right? First order differential equations involve only the first derivative. I'm going to do it over here so that people online can see. Yeah, okay. I'll go fast. Yeah. Yeah, okay. I'll go fast and highlight the ones that I need you guys to focus on. So yeah, first order versus second order, then we just need to worry about like the highest order of differentiation. No big deal there. Linear versus nonlinear is when you have these terms, the differential terms, isolated from each other. This is important for us, as you saw with the finite difference with the assignment question. Once you have these terms multiplied by each other, then you need to treat it a little bit differently. Do realize though that like the second derivative is fine. That's still a linear equation. It's just when you put it in with multiplied by something else that you get the tricky parts. Homogeneous versus non-homogeneous is what you have on the other side. If you have a function that is not a function of your dependent variable, then it's homogeneous. Inhomogeneous, you have something. Initial versus boundary. So that is something we're going to be talking about. Initial is when you only have a single value, and usually that's going to be at the beginning of your domain. So usually, and in our context, starting in like 5 minutes, we're going to be talking about it in terms of the time domain, right? So initial value is quite literally like your starting point. Versus boundary value, where you have it both at both boundaries of these things. So you can imagine that once you have both sides of these things, both boundaries, you could throw something like finite difference at it and solve for everywhere in your domain simultaneously. You can't do that with initial value problems. All you can do is step. So you have to go one and then the other and then the other and then the other and then the other. But we're going to talk about more about that soon. Okay, but that's a big differentiator. Ordinary versus partial. How many variables, how many independent coordinates do you have? One versus many. Typically, when we talk about PDEs, what we're talking about is a time as well as a space. This gets kind of funny because now you're mixing initial and boundary value problems, but we'll come to that one, I think probably next week. And then the last one, have you guys encountered this terminology before? Elliptic, parabolic, hyperbolic? Yes? Okay. I see some shakes, some opposite shakes, some perpendicular shapes. Elliptic PDEs don't feature a time term at all. Parabolic, you have one time derivative. Hyperbolic, which is a wave equation, you have two time derivatives. It relates to the propagation of information, essentially. For elliptic equations, otherwise known as stationary equations, every point is in contact with everything else at the same time. So what you have to do is you solve a consistent set of equations, which is oddly enough, that's the easy one. It's good when something is elliptic. Parabolic is stuff where you have diffusive flow. So then you have one thing that's kind of like flowing downhill, right? Downhill gradient is the way that you could do heat transport, mass transport, something like that. So that's kind of the heat equation, or more generally diffusive equation. And then the hyperbolic are the wave equations. And the wave equations is fun because now you have acceleration. Now you have a second time derivative. And we'll see how we can handle that here. Yeah. Any questions on the quick overview of those? Yeah. Initial value problems. Okay, they're characterized by knowledge of a boundary condition only on one side of your domain. Okay? It's typically, but not necessarily, valid for time-dependent equations. You could actually do it for spatial because space and time, the numerics doesn't really care. Yeah, hence the naming. So for example, you could have something like this, your first order equation, where you only have y at t is equal to 0. So that's one boundary. You could also have an acceleration type problem. So it could also be second in time, in which case you could have the displacement and the initial velocity, right? This is something falling, right? Second derivative is equal to minus g. You have something falling down, and you could give it your initial height and your initial speed. You're skydiving, right? But the key to this one is that you only have this information at one of your boundaries, not at both. Right? Just to hammer that one home a little bit, you actually are dealing with a problem that looks very similar to this right now with your heat transport equation, right? It's also second derivative is equal to some constant, q. The difference is that one's boundary value because you know something over here and over here. Whereas this particular example, you know two things over here. And you don't know anything over here. You don't know the slope or the value. Yeah. The point with this, so I do apologize for the nomenclature with this one. I set off intending to have everything in terms of t as your independent coordinate, because initial value, time, we're going to be talking about time stepping. So it makes sense that like we would have t as the I lost my train of thought. The independent variable. And then I looked into the textbooks, and every single textbook has x as the independent coordinate. So I really apologize. I will eventually go through and change these x's to t's because it doesn't really make sense, but just be forewarned. The idea is that we start off at t is equal to 0, 0 being arbitrary, of course, could be whatever, and we march through time, we time step. Several implications to this. First of all, this is likened to a time integrator. Effectively, what we're going to be doing is we're going to be taking a differential equation and integrating it from a known time to some later time. And we just talked about integration. So we know a few things about it. We know that error accumulates. Because whatever happened in the past one, there's no going back. There's no going back and correcting it. Oh, almost. There is actually a predictor corrector we're going to talk about. But after like successive time steps, so just like before we did subdivisions and then summed the subdivisions, we're going to be doing that same idea. I'll talk about that one with Runchkata. Yeah. Okay. There is a phenomenon whereby numerical noise will destabilize the solution scheme. I'll talk about that one. I'm hoping to get to that one on Wednesday. That's called stability. And that's kind of something new. That's a new kettle of fish that we haven't talked about as of yet. We haven't needed to talk about, mercifully. The time stepping has to resolve the time scale of the physics we're looking at. Right? Up until this point, we just kind of like chose a time step. We we chose a discretization step. And there was kind of like vague hand-waving arguments that your step size has to be small enough to resolve a feature of interest in order to see something. This is going to be really expounded now. Because we're dealing with time-dependent phenomenon, if you have something that's moving fast and something else that's moving slow, you're kind of handcuffed to whatever that fast thing is. Because if your time step is too big, you're just not going to resolve that fast thing. And if that's important, then you're not going to be completely shot down. It's just not going to be accurate. You're going to get massive error. The time scale might change mid-problem. Hooray! Right? We could have initial transients followed by long-term, which means that we need adaptive time stepping. That'll be on Wednesday, right? If you have something that decreases, what's an example of this? You have the exponential decrease followed by the long range. Do you guys know what I'm talking about? Okay, you get all kinds of problems where you have something that looks like a very sharp decaying exponential, and then kind of this longer term behavior, right? But if you had to sample this exponential, you have to do that very small. But now you get down here and now nothing's happening and you're still sampling at this frequency and your computer is just burning and burning and burning. So what you would want to do is much larger, ideally even identify that this has actually reached a steady state, cancel the time stepper entirely and solve the rest as elliptic, right? Next thing is that we're actually going to build a history as we go, right? Why that's important is for the next section with error analysis. What's that? It is Flex PDE. It is exactly Flex PDE. So since you mentioned it, I'm just gonna spoil the whole thing at this point. When you do partial differential equations, so you have something like time-dependent heat transfer. You would have, so this should look awfully familiar to you guys. Especially when I erase my neural network slash, is that biblical something? Forget what that thing is called. It was all over like mysticism and stuff. Anyway, doesn't matter. Let's move this guy over to this side. Plus Q is equal to di t by di little t. Now you have the time-dependent heat transport equation. This guy is elliptic. For every time step, you could solve for temperature everywhere. But the way that you get from one time step to another is actually just going to be regular old finite difference. Even with finite element, same thing. Finite difference, same thing. Yeah, that's why. That's why you're getting flashbacks. When you were doing computational multiphysics, did you guys talk about explicit, implicit time steppers, Runge-Kutta methods, anything like that? Yeah. Yeah.
Setting your time step depending on
Now you're gonna learn why. All right. Error analysis. As usual, we're going to talk about it in context of truncation error. As with other integration schemes, right? We have the local truncation error that occurs on the time step from the approximation that we're going to be using to approximate this time step, the behavior of the time step. And then we're going to have the propagated error, where we're going from one to the other, and that results in an overall drift. Wednesday, we're going to talk about stiffness and stability. Unsurprisingly, we're going to fall back on Taylor method to help analyze the errors and develop these techniques for how we're going to do it. Higher accuracy, we get to higher accuracy by approximating the higher order derivatives, right? The exact same as we've been doing with finite difference, with integration. The 0th order approximation is the slope, or the 1st order approximation is the slope. Second one, we need the second derivative information, right? If we have history, we could use that history to predict, to calculate the next time step with higher order accuracy. That's a method called multi-step methods. That'll either be on Wednesday or Thursday. But what we're going to talk about today, if I ever get to it, is a single step method that only uses the information available at least at that time step, and then takes a series of time steps, kind of like the the Romberg method of integration. To be honest, there's a lot of overlap there. Yeah, but that's why we might want to hang on to that history. But then there are other problems associated with that. That could be big. If you're solving a large system, you might not want to hold on to all your previous time steps. If you just want the final answer, do you really need to know where all your particles were in the past? Not necessarily. So there's pros and cons to all this stuff. Okay. Runge-Kutta methods are a class of techniques where the next time step is calculated from the current time step and an estimate of its slope. So we only have information from the current time step, and that's actually a lie because we are going to take like half steps and things to try and approximate those higher derivatives. But we're not looking backward in history. That's the point. That's the differentiating factor. Forward Euler, aka Euler-Cauchy point slope method, explicit Euler, is like the first way that we're going to be able to do it. All you do is you take your current value, right, y, at your time step I, and then you add on the slope. Magic, right? And that's actually kind of easy because you're actually given the slope, right? You have dy by dx from your differential equation. So all you have to do is say that your next time step is equal to your first plus whatever the right-hand side is times h. No problem. Actually, there are big problems with that. Now I'll show you with the stability one. It's just the Riemann sum. Order of error is locally h squared and globally h, right? Because we're just summing everything together. Okay. I'm not actually sure how you pronounce this person's name. Gwen, I guess? Gwen? Gwen's method says that, okay, let's do that. Then let's take that value and we'll double check it. So what it does is it calculates this, takes this value as the predictor, right? Why not at I plus 1? And then finds the slope at why not. So we go back to our differential equation. We evaluate it at x I plus 1 and why not I plus 1. And then we calculate the average slope. The nice thing, what we learned about the averages, both with differentiation and integration, like the average of the two boundaries is usually better, right? Because we're kind of canceling out the positive errors and the negative errors. That's the idea with this guy. Okay, so we do that, we take the average, and then we use the average to take the full step. So this is a little bit funny here. We're actually, no, this one isn't funny. The midpoint method is a funny one. Okay, so the idea is that this is a two-step method. We do the predictor and then the corrector. And the nomenclature predictor corrector algorithms are a big thing. We're basically just iterating. But the nice thing about this is that we could repeat this, right? We predict, we correct. We take that as our prediction, and now we correct. We take that as our prediction, and now we correct. And we're going to converge, right? Hopefully, right? Worse. This is the worst possible outcome, in my opinion. I will show you. Let's integrate this formula, right? I know I'm like jumping nomenclature all over the place, right? Now we're in primes. So we've got that, we've got our initial value, and we're going to repeat Wynn's method with 1 predictor corrector iteration and 15 predictor corrector algorithms, right? This is my code. Here's my function, right? We're calculating the corrector. And then in the case where we're going to do more of these cycles, then we just cycle this more and more times, and we output it. And I'm going to run this with 1 iteration and with 15 iterations. Do you guys want me to go through the code with more detail than this, or trust me? Yeah. What was that, sorry? Yep, okay. So yeah, so you calculate the prediction, right? Y plus H times whatever that function is. And then your next one is just Y plus H times your function at the original plus whatever your new corrector is, averaged. And if your iterations field is greater than 1, then you repeat that. You say your Y predictor is now Y next. You calculate your next. Cycle again. Y predictor is Y next. Calculate your next. Round and round and round and round until you exit. And then you assign them and print them out. Put in your initial values, your step size, and run it. So with one iteration, we get this series of integration steps. And these are the true values, just from analytical integration, right? And we get not bad. With 15 iterations, this is our progression, and these are the true values. And what this plot doesn't show you, and what I meant to get around to, but apparently I didn't, this is actually converged. So I think this guy converges in about 5 iterations, and then it just stays there for the remaining 10 till it gets up to 15. So why I said this is the worst possible scenario is because it does converge, but it converges to the wrong answer, right? We've kind of hoped and prayed that when it converges, it's actually converged to a good answer. This is an example where it doesn't, which is unfortunate because otherwise it would be pretty good. That would also mean that it would be a super short lecture. Okay, trapezoid rule, right, is kind of the, oh, this should be another indent here. Right, so like there are a lot of parallels. It's not even parallels. We're using right now a lot of the discussion that we've been talking about with the differentiation, right, and the integration schemes. So we did the forward scheme. That was the that was Euler explicit, right? Now we're doing as soon as I say like forward, you should be thinking, well, let's do the other ones. Let's do the trapezoid. Let's do the midpoint rule, right? Well, sure enough, here's the midpoint method, right? Wynn's method is kind of predictor corrector. We had never talked about something like that, but let's talk about the trapezoid. When your function on the right-hand side is not a function of the value of the unknown function, that was a lot of functions. When your right-hand side does not have your dependent variable. So if f is only a function of x, not y, then Wynn's method is exactly the trapezoid method. Because all we're doing is we don't need to do that iteration because nothing's changing. We just have x. So we calculate f at x, we calculate f at x plus h, and we average those two. Well, guess what? That turns out to be the trapezoid rule. Right? Trapezoid rule has better accuracy, OH3 locally, OH2 globally. Let's try something else. Let's try a midpoint method. So recalling that we liked central difference and central integration methods because we're kind of canceling out the pluses and the minuses, right? So this is a little bit funny. Let's do a half step. Let's calculate what yi plus a half is from this. We're literally just taking half the step size. And then we're going to find the slope at the midpoint and use that to calculate. Oh, that's not right. Sorry, my bad. Okay, and this is the tricky part. Okay, we're finding the slope. This is the slope at the midpoint, right? This term here. We're going to use the slope at the midpoint to take the full step. But I'm gonna draw this out. You're here. This is my total interval over to here, and this is the one we're looking at. We're gonna take a half step, find out what, say this was the true function, right? We're gonna take the slope here and use this slope to take the full step. We're not taking 2 half steps. Right? We're actually just taking it in order to obtain the slope and using that to take the whole step. We could also take 2 half steps, but in that case, all we're doing is explicit Euler twice with a smaller step size, which is a completely valid option. You could do that, but it turns out to actually have inferior order of approximation. Generally. I see confused looks. Anybody? Initial value problems, that the whole derivation for all this is pretty wacky. I've got to say, there's a lot of math that we're going to have to get through in the next week. I'll try and keep it as big picture as I can, and we're just going to have to power through the rest, to be frank. Okay. All of this stuff can be generalized. Specifically, these are all examples of something called the Runge-Kutta methods. Runge, I'm fairly certain, is the same as the Runge phenomenon that we saw with the high oscillations. I'm not 100% though. Okay. Pardon me?
No one had an H in its spelling.
Did it?
Yeah.
Yep. Did I spell that wrong? No. Runge's phenomenon. Yeah. Well, it's possible that I misspelled it before, so I'm a terrible speller. Awful. That's why everything's on the computer. All right. So the idea is that we're going to use, so you guys remember how with the Romberg integration method, what we had to use was like a succession of time steps in order to approximate those higher order terms, right? We're effectively going to be doing the same thing here. So what that means is we're going to take our full step, I plus 1 is equal to yi plus a something, an increment function, which gives some value of slope times our step size, right? Now the slope is like we're doing it as a slope, but realistically it's not just a straight line, right? Because we have higher order terms and things like that. This is where the math gets fun. In general, we're going to be writing this function as a sum of, this should be slash. Okay. We're going to be writing this as a sum of constants times these k functions. These are called stages. Yeah. Depending on the order of Runge-Kutta method, RK, we're going to have different number of stages, right? And they're going to look something like this. So step 1 is always f at the current point. Step 2 is going to be x plus some fraction of our step size, and y plus some function times our previous one. It's where it gets messy, right? So this is kind of like a predictor corrector, but without the iterations. So we've got our x is changing according to the fraction, and then y is going to be some like our initial y plus some kind of correction to it. And then so on, right? So the next one is P2, P3, blah, blah, blah. And then we're going to be building up K1, K2, and kind of do this weighted sum. And that weighted sum kind of looks like Simpson's rule at that point, right? We're going to be using different values in order to approximate the correct value. And actually RK3 is effectively Simpson's rule. Okay, so this is super messy. I apologize, but there's nothing I can do. The P's and Q's are constants and determine the type of RK method. I'm just going to try and get through the next section and then I'll let you guys go. RK1 is the forward Euler equation, right? That one should be fairly obvious because with just K is equal to 1, we're just done. 1 and done. The second order one gets funny The idea is we're going to be, is it actually, my clock on my computer is saying 6:16. I think that clock is wrong. Yeah, okay. Woohoo, 3 minutes. All right. Take a look at the second order RK method. So we've got two of these terms, A1, K1, A2, K2. Here's our evaluation. Here's our definitions of K1 and K2, right? We're going to be throwing like Taylor, Taylor, and more Taylor. Okay. There's some joke for like a Taylor Swift concert in here, but here it is. In the first case, what we're going to be doing is we're going to be expanding K2 in terms of our P's and Q's. And what we get is something that looks like this. This is super messy. It's the derivation. I don't expect you guys to know it. I just want to highlight that what we're doing is we're expanding Taylor expansions. We're going to plug this back into our original equation. And we're going to get something that looks messy. We're going to compare it to just a flat out normal Taylor expansion of the actual function from which we get this, right? You expand, you do the chain law on your first derivative because you have x and y, it's an implicit function, and then you match up your terms. When you match up your terms and your constants, you're going to get, at least for the second order one, you're going to get a system that looks like this. You've got your two constants sum to 1. That one is a half. That one is a half. 3 equations, 4 unknowns. Which means we have how many solutions? Infinite. Yeah. We have an infinitude of solutions. RK methods have an infinitude of solutions. Which means we get to choose. Yeah. However, any and all of those solutions will exactly integrate a quadratic problem. If the problem actually is quadratic in time or x or whatever, all of those will integrate that exactly. But your function is never going to be quadratic in time, ever. And if it was quadratic in time, then shame on you, solve it analytically. To be frank. Okay, I got like a minute here. Because we have an infinitude of solutions, certain ones are going to be better under certain circumstances than others. So we need a concise way to show these things and record them. That's called. You is you say that your Runge-Kutta method looks like this in general. You group your terms and then you write it out like here. So these are your constants inside your, and I'm not going to ask you guys to memorize butcher tableaus. Like you're going to get lists of stuff. Like, to be frank, if you guys actually need to know that, just Google it. Like nobody, some people probably do memorize this. Don't bother. The idea here is that on one side here, you have your constants inside your K for your step size. Along the bottom here is your B terms, which are the weights of your stages, right? And then you have all your coefficients in here. Why am I saying all this? Quinn's method is a Runge-Kutta order 2 for A2 is equal to 1/2. When you plug that in, you get Quinn's method with the tableau that looks like this. If you don't believe me, take that equation, plug it in, you're going to get Quinn's method. The midpoint method is another option for A2 is equal to 1. Now you get a different butcher tableau, and when you pop it in, you're going to get midpoint method. Tableau is kind of a concise way of grouping all of your constants together. So depending on what method you're determining, right, you're kind of nailing down one of these degrees of freedom, and it's going to be calculating everything else. But you're going to see when we get up to like RK4, it's going to get a lot messier. And then we're going to turn it on its head, actually. The last one there for RK2, and then I'll let you guys go, is Ralston's method. It's one particular choice that can be shown to provide a minimum bound on the truncation error. So that one's kind of nice because that at least can show you like this is as low as it could get. in which case this is the tableau associated with that. So when you look into the numerical tools and packages for this, you're going to see them specifying, okay, which RK method do you want? Do you want, okay, RK1 is Euler, right? RK2 could be any of these three, right? And you're going to get more and more and more as you go up in scale. They're going to ask for either the order and the stages, or you're going to have to pop in a butcher tableau. That's why I want to show you guys this, so that you can see where this goes. Later, we're going to talk about implicit methods, and implicit methods can also be described in terms of tableaus. But now we're going to be in this upper right-hand side. I'm going to stop there before I get more than that. I can't promise that I'm not going to return to the tableaus on Wednesday and just make sure that we know how to populate them. So that might come very in handy for implicit methods. Okay, any questions? Excellent. Yeah, it's like it's a whole bunch of math that like kind of goes nowhere until finally you get somewhere. Okay. This is the easy part, man.
Yeah, this seems pretty like elementary level. There's probably some crazy.
We're gonna get crazy on Wednesday. Yeah, you're gonna see why nobody does explicit Euler, which is terrifying. Other questions? Excellent. Cool. Yeah. One other point I remembered. In the assignment, question 3, it should have specified it's a cubic function, not a general function. In case you didn't, I neglected to put that in. I apologize. It should be a cubic function. Sorry. Yes. Yeah. Okay. So in the remaining 20 minutes, I spent a bunch of time last night going back. I wasn't really satisfied with how I presented the Runge-Kutta methods. So I went back and I tweaked a lot of the lecture notes. And I just wanted to circle back a little bit and kind of present that hopefully in a bit of a clearer way. So the whole point with the Runge-Kutta methods is you want to calculate your next time step based on the information currently available. But at the same time, you want to increase the accuracy by approximating those higher order derivatives, right? And the way that you could do it, you could do, derivative of f of x and y, chain law, blah, 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 but you don't normally have that information because it's, a differential equation or something like that. You can't get access to it. So instead, what you do is you take a series of intermediary steps and then meld those together and mush them together to get an approximation of what those higher order terms should be doing. Okay? So what that means is if you start off with the Taylor expansion, good old Taylor expansion. Honestly, this course is based on like the Taylor expansion and linear systems. And that's it. Everything boils down to it. So you start off with that, right? Because we're doing a differential equation, we have this term. We have y primed, right? And then this derivative, instead of y primed, is just like the derivatives of f of x and y. And the whole goal, and then we're substituting it by this equation here. This is the Runge-Kutta in all its glory, is this part. Obviously, what you want to do is make this sum from n through to the total number of stages approximate this expansion insofar as possible. That's the goal. That's how it works. The problem is that you can't, in an infinite case, yes, you'll be able to do that analytically. We don't have infinite time. Therefore, we have to truncate it, and we want to optimize that truncation. That's the whole point to it. Forward Euler, we spoke about. Do you want me to quickly go through this and do the whole thing? Okay, super quick. So forward Euler is the first method. It's super simple. It's literally just your value and the slope. And you calculate that and you take your step. Yeah, and then it has that accuracy because it's only one of those terms. So it's only order h squared or order h or the full domain. Wynn's method is where we're using that to iterate back and we calculate, we take that step and then we say, well, okay, what is the slope over there? You bring it back and then you do that step. Then you take it properly. It's a predictor corrector. The midpoint method. So the trapezoid rule is a special case of Wynn's method. The midpoint method is now where you're doing, this is kind of the first time that you're taking a half step. You calculate what the slope is, and then you go back and you use that slope as your full step, right? And now we're doing that whole, like, the positive error and the negative error cancel out, and therefore you get a better answer. So that kind of progression motivates the general form. So these are called the explicit Runge-Kutta methods, which is a spoiler because if I'm saying there's explicit methods, there's going to be implicit methods coming up. I don't know if we'll get to that today after that very useful but long discussion. Honestly, I love discussions like that because that's where, like, we actually are teaching each other how to do this stuff. Because I don't know, man. Like, I started using AI like maybe 6 months ago. So I'm learning a lot here. Okay, so recalling this is the general form of the Runge-Kutta, the explicit methods are ones where you do something like this. So all you're doing, these K functions are the intermediary steps. They're the function values at the intermediary steps. So K1 is f at x11, right? That's your initial data point. K2 is at x plus some fraction of your total step, and y of some meld of that slope to get to your next y value. Then you use that to calculate your next step. Now you take a different partial step and you have some hopefully better approximation of what the slope is going to be. I have a nice plot at the end of this, at the end of RK4. I'll show you guys that one. And then you just kind of complete, and then you just kind of repeat doing this to sample out that space and ideally get a better and better estimate of that slope. Why is that slope better than doing it the other ways? Look into the derivation. It's way like it goes on and on and on. People have made careers on this sort of stuff. And I'm not joking about that. People are still generating lists of Runge-Kutta methods. This the next lecture ends with a link to the Wikipedia article, that list of Runge-Kutta methods. Okay. Dun, 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 dun. Now, note that we have Kn, right? Oh, sorry. So of this general equation, we have this set of constants, A sub n. We have another set of constants, P sub n, right? P2, 3P, P3, P4, and then this Q, Q21, Q31, 32, blah, 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 right? These are vectors. Whenever you see like constant with with a subscript, it's a vector. So now we have two vectors, right? Pn and An, and Qn is our Qmn is a matrix. Whenever we see something like that, we should be thinking about these geometric objects, the matrices and vectors, which means we can slap it together in this thing called the Butcher tableau. And the whole idea of the tableau is like a concise, I don't know why it's called a tableau. Yeah. Right? The nice thing about this is that it's like kind of a concise way to describe what these methods are, especially when you go to the implicit methods. For the explicit, it is lower triangular. Implicit, it's going to be full or upper triangular. And I'll tell you guys why that is with actually some pretty nifty examples. So we can cast RK2 methods. You go through the derivation. I'm not going to repeat that one. Wynn's method turns out to be one particular choice. So sorry, when you go through the derivation, you realize that you have more unknowns than you have equations, which means you have a choice. Within that choice, within those degrees of freedom, all of the Runge-Kutta methods will behave the same up to a certain order approximation. So if you had a quadratic, all of the RK2 methods would exactly integrate that. We don't generally have a quadratic. Therefore, it's up to the approximation of those things. When we look at this particular choice, we get Wynn's method. Here's the tableau on this one, right? This is, let's see. So this 1/2, 1/2 is how you take the step, is the weighting of the different k values. K is determined by the partial step, 0 and 1, right? There's a 0, there's a 1. And this last one is the multiplier for K1 here, which is also 1. Midpoint method is also one of these RK2 methods, right? Here we have the midpoint, which is literally 1/2. That's these two. And the final one is made from 0 and 1 because it's K2 up here, not K1, right? Ralston's method, this is the generalization of the Simpsons rules. Oh, no, sorry. Ralston's method is the lower bound of the error for a certain class of methods. We can go to RK3 methods. Now we've got 3 stages, and we can do a few different. Now, actually, we have 2 unknowns. 2 degrees of freedoms in that derivation of the sets. So now we even have like exponentially more choices, of which one degenerates into Simpson's rules, right? And that's this one. I don't know if this has a name or not. It might just be RK3. But the idea with this one is that now we're doing 3 steps. And how you weight those different steps and everything is according to this tableau. RK4 is by far the one that you're going to encounter, with one caveat. I'll come to the caveat next. It is the classic Runge kata is an RK4 with a particular set of constants, which is this one, right? Notice the zeros here. And actually this matrix is even, well, it's not diagonal, but it is banded, right? It's not diagonal because technically this matrix here is missing that diagonal there, but it is, at least it's nice, right? And then what that means is when you're putting this in, the next stage is only depending on, like, for example, the half step here, K1, K2, and then you assemble K3. Finally, we get to an example. Starting at why not, K1 takes a half step, right, in that direction, according to the derivative here, samples the slope. It turns out to be here, right? So, sorry, let me try that again. So remember, the K's are the direction. K is the slope, okay? So we're starting at 0. We have our first estimate of slope, K1, and it points that way. We go over there, and now we inquire the slope again, and now it's saying, well, now I'm pointing up this way a little bit. So we repeat back from K0. Now we jump over here, which is following a half step with K2. Ask for the slope again. Now it's K3, right? So now we do the full step with K3. It gets up here, and it says, well, actually, K4 is all the way up here. So now we merge K1, K2, K3, and K4 and get up to here. And this is actually a very good approximation. This is order 5, right? And how it came to order 5 is like a textbook worth of mathematics that we're definitely going to skip. 2. Exactly like this, right? K1 is your initial guess. K2 is your next, your third, your fourth, and you're merging it together and beating it up until somehow it gives you a 5th order accurate method, right? And by somehow, I mean you go into that, you compare against the Taylor expansion with the recurrence relationships and Taylor expansions, and you line up the constants and you take the derivatives and everything like that. And that turns out to be like the go-to with one category. Adaptive time stepping. Time stepping is kind of funny because sometimes you'll have a system that's doing nothing and then all of a sudden it's doing something and then it's doing nothing again, and you won't know that. Maybe you might have an inkling that, hey, maybe something will happen, but in general, you don't know what that is, which direction is it going? Is it bumping up? Is it taking it down? Does it happen once? Does it happen 100 times? We don't know. Wouldn't it be nice if the algorithm will tell us? Okay. So, for example, a system that has a solution with this hyperbolic tangent looks like this. You've got a nice, smooth, basically linear. It's not actually linear. Basically linear behavior. You don't want to be taking these teeny tiny time steps just because you want to be able to resolve this bump here. But at the same time, if you don't take teeny tiny time steps, then you're just going to step over this thing and you won't even realize that it happened, which is also a problem. Enter the adaptive time steppers. Generally, they automatically adjust their step size based on an estimate of the error, asterisk. Come back to that one. The way that you would do it, so again, right, these methods we know are order 5 or order 4 or any of these. So we can estimate what that error is from the equation, from comparison with the Taylor expansion, right? Given that estimate, and given what we want that tolerance to be, what we want that error to be, ideally, we can adjust our step size accordingly. This is one of the examples of how you might do that. There are other examples. Basically, all you're doing is you're taking your goal divided by what you're currently at, raising that to a power, and multiplying your current time step. So if E current is bigger, then this fraction is less than 1. Less than 1 to a power is still less than 1, and your step size shrinks, right? If it's more, your step size grows. Good. Apparently, alpha is 0.2 is a good guess, according to some 1992 paper. I played around with them, but I actually resort to a different check that I'll talk about below. There are some questions associated with what you do this. Say you take a time step and you realize that the error is higher than you wanted it to be. Do you reject the time step? Or do you just adjust your time step accordingly? Do you set a threshold for both the goal time step, but also the limit? You know, I want it to be, I don't know, 1e minus 6, but I'll accept anything up to 1e minus 5. Right? So you can imagine you take the time step, you check the error. Is it greater than the limit? If so, reject. If not, accept and modify your time step accordingly. Right? There are all kinds of different heuristics you can throw at these things. There's also the possibility to throw a meta-analysis of the solver method. So explicit is useful because most of the cases you're not going to have to run a root finder to solve for the next time step. Implicit methods, you are going to have to run a root finder. Whenever you hear about root finder, you should be thinking about Newton's method, because Newton's method has what kind of convergence? Quadratic, right. If your solver is not converging quadratically, what does that mean? Is that slow? Almost. Elaborate on that one. No?
Doesn't it mean isn't it a quadratic when it's near the root?
You got it.
So it's like,
right? So what is going to be your initial guess for the next time step? Your current time step, right? If your solver is not converging quadratically, you've taken too big of a time step because too much has changed between one to the other, which is kind of a neat idea, right? Because now you're using a property of the Newton solver, right? For the implicit scheme to control your time step. But that turns out to be pretty pragmatic because you throw away any estimate of the error, or you augment it, right? You can say, yes, it's order 5, but you also have this additional test, and you can mix and match these things. So a few ways that we can calculate this error. First of all, we can change the step size. That actually turns out to be the inefficient way, right? If we just repeat the time step twice with half the time step for the second one, then we can use that. Another one is changing the integration order. And the last one is directly comparing the answers. And I'll come back to that one. So step size halving, I'm going to pick up the pace a little bit. The idea is that your error, so run an RK4 for the full time step, and then do two steps at half the time step, right? Your error is going to be the difference between those two. The more accurate one is the one where you're taking more time steps. I'm going to tell you that right now, right? So what you can do is you can define your error like that, and then you can say, you could even do this as a corrector, right? So because you know that the error behaves in a certain way, You might think that this 15 is 1 off of 16, and that's because it's 2 to the power of, what would that be, 4? Apparently, it turns out it's not. It's actually related to the constants that the RK4 is based off of. But the whole idea is that there's a proof that says you can take that error. Do you guys remember how we used the, what was it, the Romberg integration? We did the, we have the step size, and then we took that difference to make a more accurate version of that. Exactly the same. We can use that to improve that and therefore get a better answer. These are a quick demo. Yes, in fact, with 1 time step, we get this answer. With this answer, with 2 time steps, we get a little bit different. The approximated error there, and because we can solve for the analytic one, that actually reproduces it fairly well. And then you accept the improved, the corrected higher accuracy one. However, RK4 requires 4 function evaluations, right? So if you're doing 2 time steps for it, you have to evaluate that at least 8 times. And that's because you can overlap at least function evaluations. So along comes Brunchkata Felberg and says, okay, wait a second. Let's take, so RK4, again, the whole idea is that you're evaluating the function at particular steps, partial steps. Let's double that up. Let's make 2 schemes, one which is order 4, one which is order 5, that use the same steps. They extend the butcher tableau to now have 2 rows at the bottom. So what that means, so the bottom row is where you're saying that your next estimate is equal to the sum of this constant times K1 plus this constant times K2, blah, 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 blah. This has 4 terms and is therefore the order 5 one. This has 5, this has 5 terms, so this is the order 6. Now you've got the 2 orders. You can compare those, right? These are the equations that you end up using, and you compare those as your estimate. But the benefit from this one is that we've only actually evaluated the function 1, 2, 3, 4, 5, 6 times. So now you've still got that correction for the higher order, but you've done it in 6 instead of 8. And that turns out to be big payoff. This is the method of choice for most of the packaged tools that you're going to find. In particular, the SciPy implementation is called Solve IVP, Initial Value Problem. By default, but I put it in explicitly, RK45. This is what it does. It does this method, it calculates the error, and adjusts the step size accordingly. And it's so useful that they don't even do RK4 by itself. It's not a thing in SciPy. It just does RK45, which is this adapted version. Just kind of neat. Okay, super quick. You could, if you wanted, as direct comparison, and this is Mike Wellen exclusive, so AI probably wouldn't find this one. If you have yi and yi plus 1, you could just subtract those 2. Because that is the difference between those 2 values. You take the norm of that change, right? So that, sorry, you subtract those 2, and that gives you the rate of change. Take the norm of this, because nobody likes working with vectors. Depending on your norm, that'll tell you how much this answer has changed from this one. Depending on your norm in a Euclidean sense, i.e. the square root of all the differences squared, right? This is like least squared error, right? Or you could do the infinite norm, which is otherwise known as the maximum. So you could say, everywhere in my problem, thou shalt not increase by more than 1. Which is pretty useful for my type of modeling phase field because it goes between 0 and 1. So if anything's increased by more than 1, I know that I've goofed, right? I slash it and I repeat it. And then the last part is about the Newton solver. You can also, if you're throwing like an iterative method at this, you just have the solver output how many iterations it's taking, and then you catch the problem where it just kind of goes off into la la land. And instead of reaching the threshold of like 1 million iterations, you just catch it and kill it. And then you just go back and you restart it. Or even better, say you get to a divide by 0 and your solver dies, right? Well, now you use exception loops in Python, try catch, to catch your exceptions. You catch that error, say, okay, try that again, right? And now you're kind of fail-proof. which is nice. That's all I got. See you guys tomorrow.
Thank you. Good day.
You too.
I will see you on.
Excellent. So this is actually kind of a dense lecture, so let's get started. First of all, the gauntlet has been thrown down regarding the project. All the details. All the details are in that PDF for posterity. Do remember, if you are opting to do it, to send me an email. I'm asking for email so that there's a paper trail. Everybody's covered on that. Yeah, let's go. Okay, so up until how many people are online? 2 of you guys online. Third one is me. All right, whatever. Go recorded lectures. I should bring in candy. Should bring in my kids' Halloween candy. I got way too much candy. Right? Okay. Up until now, we've been discussing explicit solvers, i.e., where you calculate the next step based on information about the current step. Implicit methods instead use information at the new time step in order to calculate the new time step. It sounds kind of funny. All it means that we're going to have to do a root finder at it. There are big reasons why we want to do this, although the root finder does add significant computational expense. In order to understand why this is, we kind of have to do a bit of a demo, okay? And then talk about something called numerical stability. So the simplest implicit scheme is, again, the Euler method, but now we're going to do it backwards instead of forward. So again, we're going to assume that the function acts linearly between the current and the next step, but instead of using the slope at the current step, we're going to use a slope at the next step, right? So it looks like this. Note that f is now a function of your future step and the future value. This is nonlinear, and you have to do a root finder for it. Great. Fortunately, we know about root finders. And by the way, one of the reasons that the assignment 6 is getting more difficult is because now we're actually we've done the groundwork, and now we're actually putting it together into the real applications. So this is particularly important for anybody who's going to go into computational models in the future. Okay. No. An algorithm is numerically unstable when a small error that occurs during computation grows. Generally, stability is when little errors and little snafus are damped, right? It's actually very common. It can occur due to user choice, if you use too large a time step, or simply round off truncation error, numerical noise, discretization error, anything like that. So it's legion, right? Like you will have this problem. There will be noise in your system, okay? But you will not always find the numerical instability, okay? So numerical instability, not instability, is a property of the algorithm, not the equation. That's why we can modify, that's why we can treat it with implicit methods instead of explicit methods, and the equation solves. So let's see an example. Integrate, literally the easiest. It doesn't get any easier than this, right? Super easy, from 0 to 20, forward and backward Euler, compared to the exact solution. Does anybody not know how we get the exact solution? Right, you just integrate. That's it, and you're done. Right? You divide it up, you do the thing that mathematicians hate when you take the derivative as a fraction, you separate it out, you got 1 over dy, 1 over y, and off you go. And you make the mathematicians cry, which is a bonus. Okay. This is my first foray into using sliders. So let's see how this goes. Essentially what this is doing, it's just plotting the figure. It's showing the analytical expression here, and then it's solving it with an explicit method. So explicit is super easy, right? All you do is you take your previous time step and you multiply by 1 minus h. And the 1 minus h just comes out from the way that you derive that equation. I'll show you explicitly. We'll go through that on the later slide because that's important. By contrast, the implicit method ends up looking like this because Euler's method is essentially linear, you can rearrange it, and we don't need to use a root finder for Euler's method. Only Euler's method, because it's a linear approximation. Everything else in general is going to have to use a root finder. But for this particular case, the reason why we're looking for it is because we can just swap it around and we get something different. But note now that instead of the h term being in the numerator, it's now in the denominator. Okay, and then we plot it, and we get something like this. The dashed line here is the analytic solution, and you can slide around the time step. It's kind of neat, right? Implicit behaves, explicit behaves, no problem. Note that the explicit is getting closer and closer to just hitting the 0 right away, right? The answer never hits 0. It's an asymptotic problem, but no worries. For H0, it just hits that. When we cross that, we overshoot, right? But it's still not a problem because now we can, oops, wait. Now it rings, right? It oscillates back and forth about the correct solution, but at least it damps itself out. But at this point, you should already be like worried about this, right? Because something isn't being captured correctly. Meanwhile, the implicit solver is absolutely fine. Watch what happens, or play with the slider yourself. Increasing the step size more and more and more means that the magnitude, the ringing extends, but also the amplitude increases. Da, 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 until H2, and now the amplitude is equal. It never damps. What do you think is going to happen next? This bastard is going to shake itself apart. It will never recover the original solution. It is a catastrophic overestimate. So, why is this happening? Right? Consider the forward Euler scheme analytically. For generality, I'm just going to zoom in on here. Maybe I'm starting to show my age, but this is a bit small. There you go. Let's do, instead of doing the previous one, let's look at a little bit more complicated. Let's just slap in a constant here, just for generality, right? So we get that for some positive constant. Forward Euler is this. We say h times that evaluated at yi. You substitute in what that is. It's AYI. Group your terms, and that's it, right? Next step is equal to current times this term here. That's what we showed up there, okay? We know that this solution should be smoothly decreasing. This can only smoothly decrease if h is less than 1 over a. If it's between 1 over a and 2 over a, it'll overshoot, but eventually it'll return to the correct value. If it's more than 2, it will never find it. It will constantly be amplified. Compared to the implicit Euler, the backward Euler method, right? Now we're evaluating it at y plus 1. When we group terms, we get this nice thing, and this is valid, and this is nicely decreasing for all h greater than 0. It's there. This is a method that is unconditionally stable, and actually, in general, backward Euler is unconditionally stable, which means even if our step size is super big, let me just comment this out entirely. Yep. That's because I zoomed in. Right? So even if our time step is super big and ugly, it'll be a bad approximation. We're going to miss out on a lot of details, but it's actually still going to find the answer, which is nice. Yeah. Let's uncomment that. Okay. Numerical stability places a limit on your step size. That's the problem. There are different types of stability. There's something called A stability, L stability, and I think even B stability. It's way out of the scope of this course. Feel free to look into it on Wikipedia, but it's well, it might actually be a good topic for a project if somebody's interested in something like that. Let's see. So this example kind of like lets us develop a bit of intuition on this, right? Implicit schemes focus on the end of the time step. Like your whole goal is to find the value at the end of the time step. So you want to emphasize the properties of that value. Is it a good value? Is it a real value? So it kind of makes sense to ask for the slope at that value if that is consistent with whatever you started at. The problem is that it's more computationally intensive because anything other than Euler and you're into a root finder. Okay. Stiffness. You would be forgiven. So at the end of yesterday's class, we talked about adaptive time stepping, right? And some of you might be thinking that, hey, adaptive time stepping is going to come in. It's going to see this massive ringing. It's going to save me. I don't have to worry about this. Dead wrong. Sorry. Consider this equation, right? This one is, you have the same thing, right? Like it's a linear equation, right? It's a linear differential equation, so we can add components here. We've got a fast transient followed by this longer term behavior here, right? The analytical solution is this. So yes, sure enough, we see there's a fast transient followed by the longer behavior. If we plot it, this is what we get. It's another nice slider. This is just the limit of the plot, just so you can see, you know, big fast transient and long nice behavior. Okay. Notice that this guy finishes at, what is that? 0.01. The transient is over, let's say. Okay. So keep that in mind. Now, the stability of the fast term with forward Euler requires that h is less than 2 over 1,000. That's the equation that we just derived, that 1 over a. Right? In this case, 2 over a. Remember, 1 over a is going to keep it like a good approximation. 2 over a is a limit for any kind of convergence. Right? You might think that you only have to worry about it down here. Who would imagine? Right? Like the first time that I looked at this, I thought, well, okay, you know, I only actually have to worry about this numerical instability down here because this is the only place where the fast transient is actually relevant, right? Wrong. Even though the transient only dominates the behavior for that first little bit, it doesn't go away. It's still there. It's just not determining the overall behavior of the problem. But it's not just magically disappearing from the equation. So here's another nice little widget. This is explicit Euler and implicit backwards, right? And depending on the time step, what we see, no big surprise, when it gets up to 0.001, which is 1 over 1,000, right? That's the limit of our well-behaved system. Now we get the ringing, we get the oscillation, but okay, we still go down, no problem. And then, oh, all of a sudden we're in catastrophic failure. Okay, let's modify this and say this starts at t is equal to 0.1. Right? Oh, sorry, I'm just gonna dig through this code just really quick. This is the true answer here. That's the function that the differential equation. Explicit method, again, is a super simple one because we just need the current value and the function evaluated at the next time step. For the implicit method, we need to do a root. We need to use the root function, okay? So that's what this guy is doing. There's a reason why I'm telling you guys this. Right? What you have to do is the same as normal for a root finder. You need to define a function that you want to find the root of. Okay, so here I'm defining a function. I'm throwing it into my root finder, and that's how I calculate the next time step. Okay, here is what I get. Let's redo this now, starting after the transient, 0.01. Looks good. Okay, increasing the time step, no problem, no problem. No problem. We're about the 0.002 is when we pass that second limit. And it actually looks okay for the first little while. until the numerical error accumulates enough, and off we go again. So even though that fast transient, even though that short term, that unstable term is actually done, it doesn't dominate the behavior of your system anymore. It's still there and it's still going to tear things up. Okay? This is called a stiff equation, and they are manifold. They're all over the place. Nobody has come up with a great, agreed on definition of stiffness. This one is super easy to understand because it's just because of the manner of the differential equation. It gets much more complicated. Generally speaking, a stiff equation, so normally when you're doing one of these ODE integrals, your step size is going to be determined by whatever accuracy you want. Not for a stiff equation. For a stiff equation, your step size is going to be limited to whatever doesn't blow up in your face. Quite literally. Right? So actually, you could do some kind of like adaptive time stepper where you say, if blowing up, stop, reject, and retry. You know, that is actually a viable option. But turns out backward Euler is actually much, much better. Yeah. This is problematic because in physics, it's not uncommon to find short transients when a system reaches like a well-behaved behavior. And if those short transients are in the equation, we're gonna have this problem. So a few options, we could just ignore them, right? So for example, when you're doing elasticity travels as a wave, right? Everybody like sound. Right? Sound wave. But when you write down the elastic equations, you don't write the wave term. You say, right? You say that it's static. This is quasi-static. In actuality, what you should be saying is right? You should be saying that this is a wave equation, i.e. you have this acceleration term, which is proportional to the difference in forces. Now you get a wave. The problem with that is that that wave propagates on the speed of sound, which is fast. Meanwhile, whatever's changing your elasticity, unless you're doing a steady state, you don't want to have to resolve that. So you just cancel it. Right? No problem. Heat transport. Heat travels as a. Anybody? Take a guess. Heat does transport as a wave, but nobody says that except for a dude named Matano, I think. Right? What's that?
Then it makes sense. Use Fourier series to solve the heat equation.
Right? So the Fourier series is the Fourier in space. But I should look up this story because I've said it before and I don't remember it exactly. Apparently, the story was that Fourier, they were using it for like welding ship components or something, because everything has to be funded by military. So they were using it to weld ship components, and they found like kind of weird behavior depending on how they were like welding these things. So I think it was Fourier himself who first like kind of described that, hey, heat is actually a wave. The other way to think about this is that, normal heat equation is this. T by di temperature is equal to negative divergence of flux, right? And flux is equal to, you guys are probably like, oh God, he's doing it again, right? With assignment 6 there, right? So this is kind of the common way that you would write heat diffusion, right? This isn't a wave equation, this is heat diffusion. Fourier / Matteo / whoever else said this actually violates Einstein. This implies that the moment you apply a force, you are instantaneously moving heat in that direction. And that doesn't really make sense. What you actually want to say is that J dot is equal to, I forget the exact form,
but it's something like this. The rate of change, your flux, when you apply the force, your flux doesn't go immediately. Takes a little bit of time to get going, right? Same thing with diffusion, right? Your things aren't moving at the speed of light. They take a little bit of time to get going because they have mass. You have mass times acceleration. It's no difference here. The problem is that the time scale for this is like alpha, something like that, right? Much faster than the time scale for this. So if you did want to include that, then you would have stiffness. So, no problem. Also, by the way, if you did do it that way, you would end up with something that looks like that. And then you would get actual heat waves. I'm going to come back to this guy because that's how we're going to talk about how we would actually do an ODE that looks like with the second derivative there. It actually turns out to be super easy. I'm happy to say there are like 2 sections here where I'm going to say super easy. Hooray, because the rest is horrible. Runge-Kutta methods, I hated Runge-Kutta methods. Tell you right off the bat, never made sense to me. Hey, look where we are, implicit Runge-Kutta methods. Oh boy, okay. We are now in a position to generalize the entire concept of Runge-Kutta. The idea is we have the exact same thing and the exact same thing, but now our tableau is full. It's not lower triangular. And what that means is that these intermediary stages are defined implicitly. And that implicit part means stability. I'll tell you guys in the class and people who are watching this now, you can kind of gloss over this part because when I get to backward differential formula, that's what everybody uses. Nobody actually uses this. Wish somebody had told me that when I was learning this stuff. God, no. Oh, no. And if I am, like, you use RK45. Use the SciPy version. I have no interest in like people memorizing a bunch of tableaus. That being said, I can't promise that you won't encounter that at some point in your career. Therefore, I need to tell you what a virtual tableau is so that you're aware that it has something to do with Runge-Kutta. Okay. In explicit methods, we saw that these KNs are built recursively. So the next one is built on the previous one, is built on the next one, is built on the next one. Implicit method, surprise, surprise, that's not the case. What that means is that these intermediary stages need to be solved simultaneously. You can't solve K1 and then K2 and then K3 and then K4. You need to solve K1, K2, K3, K4, and yn plus 1 all at the same time. Fugly. Super messy. However, implicit methods are the way to go if you suspect that your problem is stiff, and you should always suspect that your problem is stiff. Yep. This whole trade-off has motivated just a plethora of this stuff. There's all kinds of RK methods. The most predominant one is backward Euler. 0th order, there's a reason why like everybody knows Euler, right? 0th order, the Butcher tableau looks like this. You can work out, follow the constants, and you're going to get backward Euler equation. The implicit midpoint method is kind of similar. The magic here is that you have to solve this equation, right? So here I'm trying to drive home the idea of the implicit solve. Your value at the midpoint is equal to your initial plus a half time step evaluated at the midpoint. You throw your root finder at that, you solve that, and you plug it in, and hey, now you've got an implicit method. Crank-Nicholson / trapezoid. We're going to come back to Crank-Nicholson in the context of PDEs. Don't worry about it right now. It's here. I've never used it in this context. There's also Gauss-Legendre. As soon as you talk about integration, you should now be thinking Gauss points, especially after assignment 6. You see that it gets messy. it gets pretty messy pretty quickly. What else can we do? Click on that link. It'll take you to the Wikipedia article that is list of arcane methods, and it just goes on. Okay, on to the good news. Systems of equations. In a lot of engineering problems, we're going to have system of equations that depend on a single parameter. For example, spoiler alert for next week's lecture on PDEs, instead of having y as a function of t, we're going to have y vector as a function of t. You remember how we discretize space into a single vector of unknowns? Now we're going to make it time dependent. The good news is that it works magically. You don't have to change a thing. All you do is you plug in the vector, you rerun basically the exact same code that's been vectorized, and because it's a numpy, it is vectorized, and off you go. No problem. Hallelujah. Something easy. Reduction of order. We've only been talking about first derivatives in time so far. If you get a problem that looks like that, where you have the second derivative, first of all, Mike's tip, be very careful, because as soon as there's acceleration, you're prone to those fast transients. Right? That's just the way that acceleration and wave propagation tends to work. You damp things out as they go. But you could throw an explicit solver, but you probably want to do an implicit solver. Nice thing about this is that you can actually decompose it. What you do, it's called reduction of order. It works in general, and even with like finite element method or finite difference method, we're still going to do the exact same technique. This is how we solve wave equations with finite difference and finite element. What you do is you say, just to follow suit. I don't know why I bother saving this. I just rewrote the entire thing. What you do is you say z is equal to dy by dt. Easy. This becomes dy z by dt. And you have another one, which is tx, whatever. You have another one that looks like that. And you're done. You plug in those values into your system, and then you just have a system of equations. Super easy, and it works. Note, because you have second order in time, you need two initial conditions, right? As you would expect. No. Example, swinging pendulum. Let's put things into motion. So, does this equation come as a surprise to anybody? No? Excellent. Okay. Note that it is an acceleration type equation. Here's our diagram. We use reduction of order to say, let's define our unknown vector y, which has elements theta and theta dot. And we know that dy by dt is theta dot, theta double dot, right, is equal to y2, right? So this is, so you pay attention to this one, guys, right? What you do is you say that this is your vector of unknowns. And then you say that this part here is equal to the second element. And this part here is depending on the first element. That makes sense. So this part makes sense. This is now your vector of unknowns. So anything that you put down here, you want to write in terms of your vector of unknowns. So you have this time derivative is equal to your function vector, right? And what you want to do is write that in terms of, okay, this is what it will be analytically, but you want to write that in terms of your vector of unknowns. So this part here is y2 being the second element, right? And this one is g sine, and of course my cursor is in, right? G sine element 1 divided by. And you say that that's equal to your function. I could have Okay, I should have a vector over that y, actually. Sorry. Yeah. All right. And then you solve. Throw it straight into RK45. Do you guys remember what RK45 means? Yes. Yes, exactly. So it's Runge Kata 4 and number 5 together solved at the same time. They use the difference between those solutions to estimate the error, and they do it adaptively. And NumPy does it completely automatically. It's a standard technique. If you go out and you're going to do explicit time stepping, you're going to be doing RK45. Okay, you put that in. I'm cognizant of the time, so I'm going to move past this here. You define your function in terms of the variables, and then you write, and then you return this vector. Right? Solve IBP. Here it is, RK45. Here's my initial guess. It just gave, AI generated 45 degrees, 0 for the initial speed. And here we go. And this is periodic motion. This is the position as we go back and forth, which is nice. Any questions so far? Nope. Is that somebody online? Nope. Okay. No. Everything that we've done up to now has been something called a single step method. What that means is that we only have information about the current time step, and we've forgotten everything that happened before. We can check that. We can move forward in partial steps, and we can query that information, but we've forgotten whatever we did previously. Isn't that a shame, right? Wouldn't it be a good idea if we saved that information? Yes, it would. The multi-step methods try and exploit that, which means that you generally have to bootstrap. Your first time step doesn't have a history, which means that you need a different technique for your first time step than your second time step until you build up that running history as you go. The idea is pretty neat. What you do is you take your ODE, you do the integral of both sides, and you get something that looks like this with a nice integral on the side. And if you remember back to our discussion about numerical integration, any kind of integration between limits just amounts to the weighted sum of that function at different points. So what that means is that you could put in, so this is the general multi-step function. It looks like this. Generally, what you say is that you have a weighted sum of your function values is equal to some weighted sum of previous solutions, of previous slopes. Looks kind of messy. We can basically skip this section and get to the good part, right? So this becomes simpler. Don't lose sleep on this part. Alpha j and beta j are the coefficients chosen for accuracy and the balance of computation. Note, and I apologize for this, this is typically written in increasing order, right? We're thinking about it as going back in time, but it's always written as going forward in time, by which I mean that we're going from 0 up to s. So the quantity of interest that we're actually trying to predict is yi plus s, not I plus 1, right? Just to put that out there. Typically, your alpha at s, your last one, is equal to 1. That's the normalization because everything else is multiplied by constants. Okay. When bs is equal to 0, bs, your final solution doesn't depend on itself. It depends on everything else and is therefore explicit. Good. Generally, one would use this technique as a predictor corrector method. So what you would do, so there's a little bit of a hazard for this, right? Because if you have a function that's going to behave like that, right? And you do that one, 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 you are very confident that your solution is here, right? It's not at all. And you would never know that unless you do a predictor corrector. So you use these to spread out there, and then you do a corrector and it jumps way up there, and maybe you have some kind of adaptive time stepping to correct for that. Because we have a constant step size out here, and because we need, if you remember integration, we need a constant step size in order to get like big bang for our buck and start to cancel out errors and get a more accurate solution. Because of that, that means that we aren't able to change our time step at each point. We can't do adaptive time stepping, or if we do, we're limited in the range backwards that we can reach. That's a big problem. It also doesn't self-start, by which I mean when you start at 0, you can't just automatically generate that background. You have to kind of like intervene, and that means algorithmic complexity. And when all that is said and done, the explicit single-step methods outperform them. They give you better accuracy with comparable, if not better, computation. So, don't bother. That being said, the implicit linear multi-step methods, the backward difference format, is what everybody does. Everybody. This is the default. This is the LU decomposition of ODE solving. Also PDE solving. Yeah. Let's see. If we say that all the other betas are 0, all we're left with is 1. I should have written that. Yeah. Okay. Sorry about that. I'll add that later. If we say that they're all 0, we arrive at the implicit one, which is called the backward difference formula and is the default for computational tools. This is what everybody uses. Okay. Starting from, I don't know why that, oh, because of the ampersand. Okay. Running out of time here. The idea is starting from this equation, you say that, hey, I could get an estimate for what di y by di x is. What I would do in order to do that is I would take my previous solutions, fit a polynomial, who remembers doing Lagrange polynomials. Good old Lagrange polynomials don't require equal time step. They are flexible, right? And then just take the derivative. Magic. When we do that, what we get are these are the first 5 of the BDF orders. Theoretically, they go on to infinity, right? And you get this nice form where you get the next time step expressed as a function of its history plus this addition term here. Note, this also appears on this side, therefore they are all implicit. And you need to throw a root finder at it, with the exception of BDF 0 or BDF 1, which is backward Euler, right? So it's kind of funny, backward Euler is implicit Runge-Kutta and also BDF because it's fun. It's like the 0, right? Everything crosses 0. Okay. Benefits of BDF are there is no requirement for a constant step size. H only appears once in one term. You don't need a constant step size. The rest is Lagrange polynomials. It is still implicit and therefore good for stiff. And you can dynamically change between the BDF orders, which solves the bootstrap problem. Because at the beginning, you do an explicit step, for example, or sorry, you do an implicit backward Euler, and then you just add it on as you go. You don't need to change a method. And these constant don't change. You just keep using them on and on and on. Anybody know why nobody really considers BDF greater than 5? Nope. Anybody else? That's a good one. Personally, I am partially favorable to the number 5 because it divides evenly and everything. Let's go to the online group. Who wants to jump up? Who's going to be first? All right, Nathan, what you got? Why do we stop at BDF 5?
I'm not sure.
Not sure. All right, Stefan, any ideas?
Very honest answer, sir. No. I don't quite
Mike-
understand this yet. Um,
Michael for the steal?
I don't
Ah,
want to randomly. Sorry.
all good. All good. All right, I'll spoil it for you. The whole concept behind this is we are taking the past few answers and doing what? What are we doing with the past few answers? What's that? Predicting? No. How?
Interpolation.
Yeah. With what? How? Actually, technically, this is extrapolation, isn't it?
Oh.
We overfit the data. We are fitting a polynomial. And would you ever fit an order 6, 7, 8, 9, 10, 11, 12 infinite order polynomial to anything ever? Nope. Bad. Bad students. Hence, you only generally go up to BDF 5. 6, 7, even 5 is kind of pushing it, but apparently it is robust because that's, again, this is what everybody does. Okay. In summary, this is a long chapter. There's a lot of math in this week. Okay, let's try and wrap it up. Explicit methods, easy to calculate. Because your next solution only depends on your previous solutions, it parallelizes very, very nicely. I give you each the current solution. You calculate one number. You calculate one number. You. Bring it back together after everybody's calculated their individual parts. Very nice for parallelization, but it suffers from numerical instability. So even though we can compute it quickly, especially with parallel systems, we can only take teeny tiny time steps in order to make sure that it's stable or have some kind of meta-analysis for adaptive time stepping. Implicit methods, computationally intensive, very much so. It parallelizes terribly. Remember that a root finder generally means linear systems. Good old linear systems, right? If you do LU decomposition, your order, remember your memory scales, your computational complexity scales as n cubed, right? So if we're doing any of these methods for larger systems, it gets bigger and bigger. If you try and throw the implicit Runge kata, now you have to calculate not only your current solution, but your previous 4 solutions all simultaneously. And now you've increased it by an order of 2 to the power of 5, right? It's terrible, terrible, terrible. That being said, you can do one time step that's literally 1,000 times longer than your other ones. And even though it computes terribly, sometimes that 1,000 is worth it. And that's like it begins at 1,000. It's remarkable just how badly the numerical stability will kill the explicit ones. Okay. Nice thing is that systems of equations naturally and readily extend these methods. Don't have to do anything special. You can do the reduction of order for the higher order derivatives. No problem. Adaptive time stepping is very important, and it can be achieved algorithmically and through clever application of these techniques. And more importantly, other people have already done that. That's why RK45 is so useful. Yes, I'm still here. I'm scrolling around. I just edited this. How can it ask me if I'm still here? Whatever. So that's nice. Just be aware that it's actually doing this under the hood for you. Okay? No. Right. Explicit Runge kata methods are very efficient for achieving accurate answers if numerical instability isn't a factor. If it is, you have to throw implicit, and then you're increasing your problem size exponentially, literally by the power of 3, right? Bad. Explicit linear multi-step methods have a whole bunch of conditions that, generally speaking, make them impractical, right? They need to be even time stepping. Well, there goes your adaptive time stepper, right? They need to have this and this and this. Implicit linear multi-step, i.e. the BDF formulas, are basically the go-to. Right? And the nice thing also is that they exploit the history of your problem for your benefit. So, moving out of the classroom, and when you close the book on this chapter, walk away with the following ideas. Okay? Know your physics. You have to know what kind of problem you're dealing with. If you don't, throw a BDF at it. That's gonna solve your problem. Might not be pretty, it might take a long time, but it will solve your problem, like LU. You solve BDF with LU, and that's going to get you 95% of the way, right? This is the default for all of this stuff. If you know your problem isn't stiff, RK45 is the go-to, and you'll actually substantially benefit from it, right? To the point where actually the numpy advice is throw RK, and if it dies, then do BDF, right? Because to be honest, it's fast enough that you can just check that. If you know your physics have an abrupt change like this, nothing will save you. You cannot, right? You can never expect information down here to predict something that is just going awry like that. So any attempt at trying to find, a higher order accuracy method is just going to miss this. In which case, backward Euler is your fallback, and is actually pretty good. To be entirely frank, I can tell you for my type of modeling that I do phase field, I frequently get points where it's like 0, 0, like any point in space is 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0. I just use BDF. I just use backward Euler everywhere. And I have a time stepper that says if you jump from here to here too fast, cut the time step, and I want to see that transition. Right. Same thing is true with pulses. So if you're doing anything that has any kind of pulses involved with it, the nice thing about the adaptive BDFs is it'll see that and it'll take it down. And that's nice. That's nice that it'll be able to do that. Okay. Any questions? So the midterm marks should now be published. If they are not published or if something is missing, please let me know. Don't forget that on Monday, we're going to do the discussion. So I'm working on the schedule. I'll post it ideally tomorrow. Then everybody will have their times. And we'll see you guys in the lab on Monday. Question? Oh, yeah. So the assignment. Oh, yeah. So I finally figured out how rubrics work on H2L. So on H2L, I think you should be able to. Can you see the rubric? Is it? Yep. Okay. So play around with it. There should be. I think when I looked at it, it gave a mark, and it was like untitled because I figured out how to use a rubric, but not how to name it. Apparently, I teach computational methods. If you expand it, then it should break down what the marking was. You see it? Oh, not for the multiple choice. So on Monday we have the midterms marked. They were hand marked and then they were just put onto it. So we'll hand them back on Monday. All the TAs will be there. They'll bring it back and just hand them.
I didn't really see your team's announcement on the presentations and stuff. When is that? I just saw it.
Is that not? Do people get notifications when I say like hi generally, right?
I just saw it.
Oh, okay.
So when do we submit like what we want to present to you, and when do you approve it, and when do we present it?
To be frank, whenever you want, but float the idea by me first, and get my approval in writing, right? Before you submit, before you go and do it. But to be entirely honest, if you just want to like procrastinate until like December 1st and then say, hey, Mike, I want to do this, we could probably fit you in. But don't do that. Like, at least like tell me beforehand or something. Any questions about